This is a tutorial to transform the Dice Fighters simulation into a Monte Carlo simulation. The Dice Fighters simulation that we developed previously runs and prints out results stating, for example, the round numbers, the number of fighters left in each of the two teams, and the final results. What we're going to be doing is transforming this script into a stochastic model and then running a Monte Carlo simulation to do many iterations of a Dice Fighters game to assess the probability of certain events, such as what is the probability that red wins. First thing we're going to do is add in a new function or a new method into the battlefield class to perform an entire simulation execution. In this case, I'm going to define a new function called simulate and pass in self parameter for the battlefield that will actually be performing the simulation. And in here, I'm going to move in some of our previous code that performed some of the analysis. So specifically, I'm going to cut and paste this segment of the main method and making sure to indent it to the proper level of indentation. And because now we're attaching this method to a particular battlefield, we can replace our previous variable battlefield with the self attribute. So as long as this particular battlefield's red team size is bigger than 0 and its blue team size is bigger than 0, advance its own round. We're going to remove this print statement to avoid gumming up our console with lots of text, and instead return the result of the winner of this function. So after this while loop finishes, we know that the game has played out to its completion, and we'll use some of these same tests as before. I'll actually copy and paste them in as well, making sure to indent them to the right level of indentation. If its self's red team size is bigger than 0, we know that the red team has won, and we can actually return that as the value. Return self.redTeam. So the red team is an object of type team. It gets returned as the result of this function in this case. Similarly, if this own battlefield's blue team size is bigger than 0, we can return self.blueTeam. And otherwise, if there's no winner, if both of the teams have less than or equal to 0 fighters left, we can return the none type, which is a special type representing that there's no winner. So if we run the script as it is, we don't really have any body down here in to execute, but we did instantiate a battlefield. And we can take, for example, this battlefield and run the simulate method on it. And what this returns is one of the teams that was the winner in this particular case. But we don't necessarily know which one from the console. We'll have to check that in a script. So in a Monte Carlo simulation, I'm just going to remove this for now. Well, to check which one it is, we could inspect this battlefield, look at its red team, for example, and look at the size of the red team, which is currently 0, and which means that the blue team is likely the winner, and indeed it was. In this particular simulation, the blue team ended with 2 players, so it would have been the winner. So transforming this to a Monte Carlo simulation, we want to do a couple of things. First, fix the random number seed so we can get consistent results. So maybe I'll seed the random number generator with the value 0. Then I also want to identify the number of samples or the number of trials to execute. Let's start with a relatively small number, 1,000 trials. And we want to store the results of certain observations in arrays. So maybe the observations we want to make are the event whether red wins. So instantiate a numpy array filled with zeros of length, number of trials. And maybe some other events we may want to observe are if the blue team wins and if there are ties. Okay. So then to perform a Monte Carlo simulation, we want to iterate over our desired number of samples, so for a temporary variable I in the range of the number of trials. What we want to do is essentially perform a battlefield simulation. So create a new variable battlefield, set it equal to an instance of a new battlefield object, and then from this battlefield, run the simulate function and store the results of the simulate function in a new variable called, we'll call it winner. So this winner variable is taking on the result of the simulate function, which will either be the red team if it's the winner, the blue team if it's the winner, or none if there are no winners. So to assign the outcomes of the observations for this Monte Carlo simulation, we want to perform a couple of tests. Check to see if the winner is equal to the battlefield's red team. Then we know that the red team wins for this trial. The ith trial is true, or 1. Otherwise, if the winner is the battlefield's blue team, we know that the blue wins for the ith trial is 1. And the final case is if it's not one of these two, we know it's the third case where the ties in this ith trial is 1. Oh, looks like I have a typo here, battlefield. All right, so I can run the script as it is, and it will record the observations in these arrays. Red wins is this array of zeros and ones. Same thing for blue wins and ties. So now we can start to analyze these results. I can start with just some simple print statements at the end of my simulation. So I can print, for example, a message saying that we've completed some number of trials, where I can format the string to fill in the curly brackets with the number of trials. We can print out our estimated probability of a certain event, like the probability of red winning. And let's add in a current estimate, 3 decimal points of a floating number. And we'll format that with the mean of the red wins data. And do the same for the other two probabilities of interest, probability of blue winning and the probability of no winner. The mean of blue wins and the mean of ties. All right, let's run this real quick. See some of our outputs here. The probability of red winning appears to be 78.9%. Probability of blue winning is about 20.8%. And the probability of no winner appears to be about 0.3%. Now we can add on some additional information to compute confidence intervals with a couple of extra lines of code. So the first thing for dealing with confidence intervals is to identify our significance level. So our significance level could be, for example, 0.05 to give a 95% confidence interval. Then we want to compute our critical z-score. And to make things a little bit easier, I'm going to import the scipy.stats function or library and refer to it as stats. So then our z critical score is stats.norm for the normal distribution. PPF is essentially the inverse cumulative distribution function. We want to compute the 1 minus significance divided by 2. Significance divided by 2. So just run this for example and look at our z crit score, which is about 1.96. So that looks good for a 95% confidence interval. And then our confidence interval for these 3 cases can be computed with the z critical score times the standard error of mean. So I'm just going to add that in down below. So the probability of winning for red is the mean value plus and minus some other value, which I'm going to format as a 3 decimal point floating point number. And in the format option, so I have the mean of the number of wins and then the z critical score times stats dot standard error of mean of the red wins. And I'll do the same for the other two. So display number of blue wins and z critical times the standard error of mean for blue wins, and same for the ties. Also making sure to add in this other little bit of text to display. Okay, so running this test, we can see that we've completed 1,000 trials. The probability of red winning is 78.9%, plus or minus 2.5%, and similar values for the other three. Now we can see, for example, that if we increase our number of trials, so let's say go to 10,000 trials, takes a little bit longer to run, our probabilities of these events look actually pretty consistent with our previous estimates, but our 95% confidence intervals have shrunk greatly with the addition of those extra 9,000 trials. One last thing we may be interested in doing is creating a visualization or a plot of these results. So for example, we can create a new pie plot figure, and in that we want to display the current estimate, for example, of these three estimates throughout the course of these 1,000 trials. So I'm going to plot as the x-axis the range of the number of samples. So 1 plus numpy a range num samples gives us an array from 1 to 10,000. And as the y variable for these plots, looks like I also need to import the matplotlib. Let's see, import matplotlib.pyplot as plt. Right, and I didn't call it num samples; it should be num trials. Okay. The y value for this is the current estimate of the mean at each of these points in time, which we can say, for example, is the mean of the red wins from 0 to I, and then repeating that calculation for I in the range of the number of trials, and surrounding that result in brackets to generate a new list. And this one, I'm just going to make it a red line with a label of probability of the red team winning. Do a quick check. So this is rerunning the full simulation. Looks like the, typed 1 instead of I. We want the mean number, I'll just run these two. Oops. One thing you can do in PyPlot is you can add in a hashtag and then 2 percentage signs to be able to run one of these blocks as just a small block, so you don't have to rerun the full 1,000 trials again. So here's our figure of our current estimates of the red team winning. It starts quite high, and then as many more samples get computed, it starts to drop down. Let's just add in some other X label. So this is the trial number. The Y label is the probability. And then we'll add in a legend in the best location. Oops. Right. So here's our revised plot, starting to look pretty good. We can add in these other variables of interest. So the probability of blue winning is the mean of the blue wins from 0 to I. And let's make it a blue line. And probability of ties. Let's make it a black line. I'll just run this module. Okay, so we can see that again, the red team wins. It's evening out to somewhere around 0.7 or 78 or 79%. Blue team is just over 20%, and the number of ties is very, very small. We could also overlay on this plot the confidence interval ranges as estimated for these various events. However, that plotting feature I've covered instead in the Comte de Buffon